Welcome! I'm going to be running through some steps you can take in order to get up and running with Tensorflow via Anaconda on the Andrena GPU Cluster at Queen Mary. To log in, we assume that you've requested an account and followed our other documentation to set up SSH keys appropriately. If you need any reminders, then the Andrena pages on our documentation site have some information for you, including the hostname to log into. So let's begin. In a terminal, I'm going to run the SSH command, connect to andrena.hpc.qmul-its-research, and then I'm going to supply my login account name with the -L option. In this instance, I'm using an account name called learner. I also supply the -A option to forward my SSH keys to make it easier to connect to other machines once I'm logged into the cluster. I enter my password, and now I'm logged in. As we will be installing a bunch of packages via conda, now is a good time to check my quota with a qm-quota command, and in this instance we're using a very small amount of space. Now that we're logged in, let's load the Anaconda application into our environment with the module load command. Then we're going to create a new virtual environment in which we can install packages. I use the conda create command, supply a name for the environment, which I've called Tensorflow, and added the quiet and yes options to optionally reduce the amount of information printed on the screen during this process. When that's complete, I then activate the environment I've just created and notice that the prompt changes to show the name of the environment that's active. To run TensorFlow jobs on the GPU, I need to install the conda package called TensorFlow-GPU, which I do with the conda install command. This can take 1 or 2 minutes, so I've sped up the process slightly. And when it's complete, I can use the conda list command to show all the packages in my current environment. We've prepared our environment, now we need some actual code to run, and we need to provide a job script to tell the scheduler what resources we require and what commands will be run in the job. I'm currently logged in to the Andrena front end and I'm in an empty directory. I have a Git repository with some example code in. I'm going to clone that repository into my current directory to grab those files. There are of course many different ways I could get these files onto the machine. With the repository now cloned, I now have an examples directory with the files in it. The first piece of sample code, mnist simple, uses the mnist dataset to perform some training using the Keras high-level API for TensorFlow. Next, we need a job script. We've provided a very appropriate example job script on the Andrena page of our documentation website. So let's copy-paste this script into a new file created with a text editor and make some minor modifications appropriate to the job that we're going to be running. So while we're editing the file, let's get our commands fixed. The environment I created was called TensorFlow, and the Python script I downloaded was called mnist_simple.py. Now conveniently, we've standardized all the resource requests for GPU jobs, and the resources specified in this example script are just what you need for a single GPU job. 8 cores, 11 gigs of RAM, 1 GPU, and you're specifying the Andrena cluster to run on. So when it comes to the commands, we're going to load the Anaconda module, activate the environment, then run our Python code. So let's save the file. Our job script is ready to submit. We do this with a qsub command and the name of the job script file. We get given a job ID which is unique. Once a job has been submitted, it will either run immediately or be queued until resources are ready. The qstat command can tell you the status of any queued and running jobs. And in this instance, our job is running straight away, and it tells us that we're running on a GPU node called SBG16. A new file will be created to store any output from this job. This file is named with the suffix of the job ID for that job. Let's use the tail-f command to see any new activity on this log file. This is going to take a little while to get started, so in the meantime, let's take a look at the GPU activity on that node where our job is running. We'll be using the NVIDIA-SMI command to monitor the activity. We can see there's no activity at the moment and no processors attached to the GPU. Now there's been some activity in our log file, and you can see why it's important to check these log files to see if there's been any errors or if the GPU has been successfully assigned. It's quite common for a small misconfiguration in your code to result in the job running on a CPU instead of a GPU. Apart from wasting resources for someone else, it will also cause your code to run very slowly. Anyway, let's go back to the NVIDIA SMI output, and you can see now that my Python process has attached to the GPU. I've been allocated exclusive use of device 0, however you can see there is no computational activity on the GPU yet. This is also a good time to note that if you request more than one GPU for your job, you should always verify that every GPU is successfully utilised by your code. So good things to check for are maybe that the process does not attach to the device, or that process is attached to the device but just using 0% GPU for the whole job. After the initial preparation, the training steps have begun, and we should expect to see activity on our GPU now. And here we see GPU 0 is using about 19 or 20%. In this example, I'm only running a single job, but you're totally free to queue up as many jobs as you like, and they'll be run on GPUs if they're available. Our job is now complete, and qstat confirms that there are no jobs queued or waiting. Let's run through another example, one that requires another package to be installed in our environment, and also one that produces image files as a result. This second example can also be found in the repository I cloned earlier. Code will perform image recognition training on a dataset of fashion items. So as we can see from the code, we also need the package matplotlib, which isn't included in the original environment, so we need to add that to our existing environment. We load the Anaconda app again, we activate the environment, and then we use the conda install command to install the required package. -y on the end allows me to confirm the installation without additional interactive input. After the installation of the package completes, we can deactivate the session with conda deactivate. The job script we'll be running is very similar to the one that we've just run earlier, so let's copy that and make a small modification to it. So the setup is almost exactly the same. I'm keeping the same environment name now that I've installed the extra package into it, and I'm just changing the name of the Python code on the last line. After checking if I have any other jobs waiting or running, I then submit the job using the qsub command and the name of the job script. Resources are available, and so the job starts running immediately. And we can see that an output file has been created and output is already being produced. Let's tail that log file now. The Tensorflow logs appear to confirm that the process is attached to the GPU, but let's confirm that with NVIDIA SMI. On this occasion, I've changed the reporting update interval to 5 seconds. This example is on an otherwise empty node, but what if it's a busy node where other users are using GPUs? How do I know which process is mine? For example, here's a GPU node where 3 GPUs are currently in use. It's not immediately obvious which process belongs to me. We can use the top command to get a list of processes running on the machine and their owners. The default view will show you a list of processes and owners, and also useful information such as CPU and memory usage. I've highlighted the process belonging to the job we submitted. There's a Python process using 1.1 gigs of RAM, 100% CPU of one core, and also there are moments where I see it switching from running to D state. A D state often signifies that the process is blocked waiting for some storage activity to complete. You can reduce the effect of this by using scratch space, since it is designed for highest performance. Now you'll notice that the process ID in the NVIDIA SMI output matches with the process ID of our process in the top output, so we've confirmed that this is our process attached to the GPU. In our other terminal window, let's go back to the log and see how progress is getting on. And we can see that training on the GPU has just begun. Quickly checking our GPU activity again, we can now see that the GPU is being used for the computation. And finally, our job completes. You can use Ctrl+C to stop tailing the logs and to exit the NVIDIA SMI. And the qstat command shows that there are no running jobs, so our job must have completed. Finally, I mentioned that this code produced some images at the end of the job, so I'm just going to use FileZilla on my own machine to copy the files back and inspect how the training went. In the output produced, I can see that in the bottom left there's a red bar showing that one of the items was misclassified. So for your first few cluster jobs, I'd recommend this kind of approach to checking how much GPU your job uses, if it's using GPU at all, how long they tend to take when they're running on the GPU, this kind of stuff. And then over time you'll get a good idea of that, and you won't need to check so meticulously when you have confidence that your jobs are running well. But in the beginning, it's good to check these kind of things so you don't make errors. Please check out other videos for similar tutorials and content.